Hey everybody, sorry I couldn't be there today, but we've got some really exciting stuff that we are starting. So this next chapter is going to be on linear functions, and you've already looked a little bit at tables that involve some linear functions, and now we're going to go into the basic linear function, and that's direct variation. And what direct variation means is a fancy way of saying it would be that y varies directly as x. And all that means is that x and y are related through some multiplication process. And there's a pattern that forms between points and between input and output in the function. So if you ever see y varies directly as x, all that means is that we're going to have a function that looks like y equals mx. And sometimes instead of m, they might write it as y equals kx. Either way, that middle term, right now, we're going to be calling it the constant of proportionality. So a nice giant word to start us off in this chapter, the constant of proportionality. Sometimes it's called m, sometimes it's called k. I prefer to use m because it's going to lead to our next topic, which is slope. But a lot of times when you're working with direct variation, they'll call it k instead for some reason. So you might see it either way, but just know whatever this value is in front of that x, that's the constant of proportionality. And that's the thing that I'm talking about that makes the function vary directly. That's that multiplication factor, that constant that we're multiplying by, or when we're looking at a table, that's the constant pattern that we're seeing. And in proportionality, we've already seen there's a word in there that we already should know. There's that word proportions. And that you should know that's dealing with some fractions and equivalent fractions that we need to look at. So we're going to dive right into direct variation by looking at some examples. All right, so in this first example, we're going to look at a couple different things. Now, this example here should seem pretty obvious to you guys. The input is 3, the output is 12, the input is -2, the output is -8. And then we need to figure out, okay, if we input 1, what are we going to get as our output? So when we're dealing with direct variation equations or direct variation functions, we should already be thinking, okay, there's got to be some sort of pattern going on. And actually, there's going to be two patterns that form. The first pattern, and this should be a little bit more on the obvious side, is moving from x to y. When we move from x to y in our first two values here, you should notice that there's a constant pattern or a constant of proportionality in that we have to multiply by 4. 3 times 4 is 12. -2 times 4 is -8. So we're already seeing that this 4 is the constant of proportionality. So is that constant of proportionality, which means that down here, this last one is pretty easy because all we have to do is multiply our input of 1 by 4, and that gives us an output of 4. And we can keep going with examples. If I inputted 2, I would get 8. We already said 3 goes to 12, 4 goes to 16. There's a pattern that's forming. Now, I said that 4 is the constant of proportionality, which means that if we write our equation in the form of y equals kx, where k is this constant of proportionality, then our equation would just look like y equals 4x. So direct variation is pretty easy. It's kind of the basic or the backbone of linear functions. It's the most basic type of linear function that you can have. Now, the other type of pattern that is forming deals with change over the inputs and change over the outputs. So if I look at these bottom 4 inputs versus the bottom 4 outputs, on the left side, you can see that there's a pattern that I used where I went up by 1. I added 1, I added 1, I added 1. Now, in order for it to be direct variation, and we'll figure out that also in order for it to be linear, that same there has to be a similar pattern on the right side. It doesn't have to be +1, but it has to be a consistent pattern of addition or subtraction on the right side. And from 4 to 8, we have to add 4. From 8 to 12, we also have to add 4. 12 to 16, we have to add 4. And if we look at that as a fraction, as the change in y over the change in x, and I'll write that out up here. If I look at the change in y over the change in x, then I've got my change in y is 4, my change in x is 1. And would you look at that, 4 over 1, that's the same thing as 4. Those two things are going to be the exact same every single time that you're doing direct variation. The change in y over the change in x is going to be the same number as that constant of proportionality, that constant number that you're multiplying all of your inputs by. And that's the special thing about direct variation, is that constant of proportionality is the same as the ratio of the change in y over the change in x. And this is why it's called the constant of proportionality. Because if you looked at the pattern up here, how do you get from -8 to +4? So think a minute, -8 to +4. Well, -8 to 0 would be 8. Plus 4 more, that would be 12. How do you get from -2 to 1? Well, you add 3. And if you look at that, the change in y over the change in x, that's 12 to 3. And this is where our proportion comes in. 12 over 3 is the same thing as 4 over 1. Those are equivalent ratios, equivalent fractions. That's why it's called the constant of proportionality. It's constant because it's the constant thing that we are multiplying our inputs by. And it's of proportionality because we can make those proportional ratios. We can make the change in y over the change in x be the same fraction. So we're going to look at a few examples of where that comes in handy. All right, so one of the biggest things that you can talk about with slope, with constant of proportionality, with linear functions in general is speed. So in this problem here, we say, Mr. G drove the white bus 270 miles this season. He drove a total of 6 hours. Write an equation to model his average speed. All right, so when it's dealing with speed or average speed, that's where you should be thinking of constant of proportionality. That's where our K comes in, that constant of proportionality. So first thing that we need to do is we need to set up our ratio for speed. So speed, how is speed measured? Well, we're dealing with miles and hours, so we'd say it's in miles per hour, miles per 1 hour. So we want to get it down to where we get how many miles per 1 hour. So we know that we drove 270 miles, and we drove for a total of 6 hours. Now, we just need to figure out, okay, what is that in terms of 1 hour? Now, we could go through and set up our proportion. 270 divided by 6 is equal to x over 1. And we could go through, cross multiply, and solve it. But the nice thing about the constant of proportionality and the nice thing about direct variation is that I don't have to go through this process. All I need to do to figure out my speed, or my average speed in this case, is to divide these two numbers. So I'm going to do 270 divided by 6, and I can do that in my calculator, and that gives me 45. Now, don't be fooled though, because that just means it's 45 over 1, which means that it is 45 miles per 1 hour. So 45 miles per hour was the average speed. So Mr. G, I drove the white bus at an average speed of 45 miles per hour over those 270 miles in 6 hours. That doesn't mean the entire time I was driving the bus I was going 45 miles an hour. That just means that was the average speed that the bus was going. Now, we need to make sure that we're answering the question here. It says write an equation to model the average speed. So in this case, we're still dealing with direct variation, so we want to plug it in to y equals kx. And we just figured out that our k value is 45, so we would have y equals 45x. Now, just to make sure that we're clear, this equation gives us certain information. All right, we can plug in different things for x, and x, that would give us an output. So if we inputted different things for x, we would be inputting the number of hours, and we would get as an output the number of miles. And you could think about that in this original ratio that we created, because anytime that we're creating a ratio for the constant of proportionality, we're deciding what's our input, what's our output. The outputs are on top, so we have the output over the input. So in this equation here, that means that we have the miles, m, or we could say d for distance, is equal to 45 times the number of hours, h. So depending on what the question is asking, I always like to use variables that make sense in the context of the problem. If you're more comfortable going with x and y, great, go with x and y. I tend to like to use variables that go along with what's going on in the problem, because I tend to forget what's going on in the problem. This is a good reminder, oh, I'm dealing with distance and hours. Otherwise, I get caught up in doing the math and forgetting about the real world application. All right, one more example. Alrighty, last example here, as we're getting closer to October, or I guess it's getting close to the first day of October. I wanted to do a Halloween candy example. So this one says Snyder's is selling bags of Halloween candy as 2 for $17.60. Felker's is selling it as 5 bags for $47.75. Which is the better deal for 1 bag? So you probably already have a way of figuring this out on your own. But what this essentially comes down to is 2 different direct variation functions. And one thing that makes a direct variation function direct variation is that if you have 0 as your input, so if you buy 0 bags, it should cost you $0. So if you think about that in terms of a graph, think about what point all direct variation functions need to go through. If you input 0, your output should be 0, which means that all direct variation functions should go through the origin. They should all go through the point 0, 0 on the graph. So anytime that you have to actually graph something that's direct variation, you should notice that it goes through that point. But moving on to this problem here, we got 2 different things going on. So I'm going to do it in my 2 different colors here. I'll do Snyder's in green. So Snyder's in green, and then I'll do Felkers in blue over here. So let's look at Snyder's first. So it's saying that it's selling Halloween candy as 2 bags for $17.60. So 2 bags for $17.60. We got to figure out that constant of proportionality. So I'm going to put the dollars on the top. $17.60 per 2 bags. And I'm going to find that, and what we call this is a unit rate. We're thinking, how much does this cost for 1 unit? And the unit in this case is bags. So how much is Snyder's charging as a unit rate? Well, all we have to do is divide those 2 numbers. So I got my calculator out. I'm going to do $17.60 divided by 2, and that gives me 8.8. So it would be $8.80. Now, keep in mind, remember that's $8.80 per 1 bag. And if I wanted to write that as an equation, I would say that the cost is equal to 8.8 times the number of bags. That would be my direct variation equation. Now I'm going to look over at Felkers. I'm going to do the same thing. I'm going to put the cost on the top, so that $47.75. On the bottom, I have 5 bags, and I'm going to divide. $47.75 divided by 5 gives me 9.55. So $9.50 per 1 bag, which means my equation for Felkers would be C equals 9.55 times B. C equals 9.55B. Now all we have to figure out, okay, which one's the better deal for 1 bag? And this is really easy because you just have to look at that constant of proportionality. An obvious choice would be Snyder's. Snyder's would be the better choice at $8.80 per bag. And maybe sometimes you're going to get a question that says, how much of a better deal is it? Well, then all you need to do is subtract $9.55 minus $8.80 to get your answer. All right, so we've gone through a few examples together. Now it's time to practice on your own. You've got a Delta Math practice assignment, but that Delta Math practice assignment is not due until Friday. So you've got a couple days to work on it. You'll have another Edpuzzle video tomorrow that goes through some of the other concepts that are talked about in the Delta Math assignments. Other than that, happy to see you guys on Friday. Have a great day.